on this computer. Great. All right. So today I'm going to be talking about the very last topic of this class, which is going to be. Let me bring up my iPad. All right. So today I'm going to be talking about the topic of subtyping, and then I'm going to be talking about the topic of variance. So this is usually not typically it's not in syllabus. So this year it's not going to be in syllabus. Uh, Syllabus is everything that I covered before Thanksgiving. So syllabus for final is everything I covered before Thanksgiving break, or before the Thanksgiving break, which includes last Tuesday's lecture, which is also not going to be in syllabus, but it's going to be part of your assignment 10 that I just posted. It's based on last Tuesday's lecture. All right. But for the final, all you have to worry about is stuff until object oriented and traits, which is the very last topic that's on the final. Still, I think this topic is important. Especially if you're ever going to consider making a career out of developing in Scala, which a lot of companies do these days. A lot of big companies like Apple and Twitter, they have huge development teams that work especially in Scala. So it's very important to if you're ever going to do that, since we spent the semester doing Scala, it's very important to wrap up some of the important topics in Scala, which are very specific to Scala and the way Scala does things. But these concepts are definitely more general than Scala. So I'll explain a little bit. Okay, so far we've been looking at type systems. So we've been looking at type systems, and we've been studying our types in the language letters. For example, we studied types like num. We studied bool was a type in letters, and then you had function types like num arrow bool, bool arrow bool. So these were all the kinds of types we had in a language like letters. And then you had higher order types. You had num arrow, bool, things like that. So you had higher order types. All right. Now, the important thing is these types were not related to each other. So numbers are numbers. So numbers are the numbers like from minus infinity. Well, that's not quite a number, but you have all the negative numbers. You have all the negative numbers, minus 10, minus 9, 0, 1, 2, 10, and goes on forever. So this is the set of values that you can have for type num. For type bool, we said we had the value true or false. Similarly, num arrow bool is the set of all possible functions from input num that an output bool. So there's too many to write down, so I'm not going to write it down. All right, so we saw this, but interestingly enough, there were no relations between the types. So there is absolutely no relation between a num and a bool, or a num arrow bool and a bool arrow bool, and so on. So types are completely unrelated. Whereas in a language like Scala, we have a very rich type system. So we have a very rich type system. And in this type system, you have your inbuilt types. So you have your inbuilt types like your int, your unit, your double, float, your char, short, byte. So you have all these types, right? You have all these inbuilt types, so to speak, inbuilt types. I mean, there's nothing special about them, but these are already types that are already provided to you. String is an example. String, list, which is a parametric type. You can take in list of any type, right? So you have these types that have been provided to you already, and then you have your user-defined types. And user-defined types in Scala are primarily going to be your classes, the objects that you create, the classes that you define are going to be your types. So class foo, class bar, these are things that I define. And this includes your case classes as well. After all, a case class is nothing but a class with some extra stuff that's already given to you, right? So you have your class. Now, the interesting thing is there is a type hierarchy. So So you can create type hierarchies, and the idea here is you can have classes that inherit from each other. So you can have foo and you can have bar, because bar extends foo. So you can have these inheritance relationships. And in fact, you have other kinds of relationships as well. In Scala, you have this class any, which is a super type of like a class like int or unit. These are all in subtypes. These are all subtypes of a type called any. And anything you define, like let's say your foo and your bar, are also going to inherit from any. Okay, so Scala has a rich type hierarchy, and we call these relations subtyping relations. Subtyping relations, and this is called a subtyping relation. But this also happens to be an inheritance relation. Okay, and this is an example of a subtyping relation. So what does it mean to be a subtype of a different type? So when I take two types, T1 and T2, and I say that T1 is a subtype of T2, what does it mean? So what does it mean to be a subtype? Okay. Informally, you can say that if you look at all the values V1, which are all the values that can be regarded to be of type T1, and you can say V2 is all the values, the runtime values that you obtain of type T2, then what's the relationship that you have between V1 and V2? So this is the set of values, the set of values of type T1, set of values of type T2. What relationship would you expect between values of type T1 and values of type T2? Anyone? Oh, so my question is, remember, you can associate types with values, right? So for example, the type num in lettuce is associated with all these values, -10, -9, 0, 1, 2, 10, all the numbers, right? Informally, you say the type num is associated with all these values. Likewise, the type bool is associated with all these values. All right. So now I'm interested in relationships between types. So I'm interested in a particular relationship called a subtyping relationship. All right. And what I mean by subtyping relationship is I want something like this. The set of all values V1 that you think about for type T1 must be a subset of the set of all values V2 of type T2. Okay, so that's something that you want to expect, right? So informally, you want a subtyping relation to say that anything of type T1, so you want to say anything of type T1 is also of type T2. So so you want to say anything of type T1 is also of type T2. So that's something you want to call a subtyping relationship. Uh, but this is too specific. So as an example, idealized example, and I will tell you why this is not the case in real life. You want to say that the type of natural numbers, you would like to say it's a subtype of the type of real numbers. Obviously, natural numbers are a subset of real numbers, right? So I would love to say that natural numbers are a subtype of real numbers. Is that okay? Just because I would say that the set of natural numbers is a subset of the set of real numbers. Okay, this is something I would ideally like to say. Okay, so that's one way of thinking about subtypes, but it's actually quite misleading. And today I'm going to tell you how to step back from this, and think about subtyping in a different way. Okay, so today I'm going to try and dig into the definition of what is a subtyping relationship. All right, and I'm going to make you think about subtyping in a different way. Okay, and what you will see is a subtype relationship is not necessarily a subset relationship. Okay, so I'm going to try and piece apart the meaning of these two things, so it's going to get a little bit philosophical. Okay, but let's talk about this. Right, so v1 in this case, to answer Laura's question, v1 in this case would be the set of natural numbers, and v2 in this case would be the set of real numbers, and obviously natural numbers are a subset of real numbers. Is that okay? Good so far, Laura? Okay. Now this is actually not quite accurate. So this is not quite accurate. So I don't want to, spend half the lecture creating a picture and then spend the second half of the lecture destroying the picture. So this is going to be not quite accurate. And you will see today why it's not quite accurate. All right. So we are going to see that. So what we are going to do today is we are going to use a different definition of subtyping. And we are going to borrow from a principle we have seen before, which is called the Liskov substitution principle. And the principle says, and we saw this in the context of inheritance of objects. Today we are going to use the same principle for subtyping. So what we are going to say is T1 is a subtype of T2 if and only if, okay, and this is the principle, this is what it says, wherever a value of type T2 is required, T2 is required, a value of type T1 can be provided. Okay, whenever a value of type T2 is required, a value of type T1 can be provided. Is that okay? So we are going to use this principle, and this is called Liskov substitution principle. We've already seen this in the context of inheritance. So we said instead of subtypes, there we use subclass, right? So there we use the term subclass, right, or subclass. In other words, T1 inherits from T2, or we are also saying is a subtype. All right. So now we used this previously for just for subclasses, just for two classes, T1 and T2. Now today I'm going to use it for types, arbitrary types. All right. So I'm going to start with simple types, and then I'm going to talk about function types and so on. All right. So what we want to say is wherever a value of type T2 is required, a value of type T1 can be provided in its place. And I should be able to use that value without worrying about it. Okay. So as an example, let's revisit this definition that natural numbers is a subtype of reals. So is a subtype of reals. Okay. So the question is that really true? Okay. So then the point is, what are we going to do with numbers? So then the point is, what are we going to do with numbers? So suppose we have a function to add two numbers. So a function plus to add two numbers. So that's going to take two real numbers and return a real number. Okay, so this function is just the addition function, the function that we've learned in grade school that we know and love. Let's say the function multiplication is going to take two real numbers and return a real number. Right. So Kai makes a good point, right? Anytime you need a real number, you can always plug in a natural number there. Is that okay? Good so far? What about the other way around? No, right? Can you give me an example of an operation that's defined over natural numbers that you may not be able to do over real numbers? Modulo. Very good. Excellent, Kai. Thank you. So you can see that, right? So any operation that I can define over reals, right? Any operation that I can define over reals, e to the x, sine x, cosine 2 pi x, uh, 1 by x plus x squared plus 1. So there are so many of these functions that I can define over the reals, and these are functions that take in a real number and return a result. So wherever I need to use a real number, I could always say take the natural number 5 and think of it as a real number 5.0. On the other hand, the reverse does not hold. Real numbers are not a subtype of natural numbers because there are operations involving natural numbers that could never be done, or that could not be normally done using real numbers. Another example would be factorial, right? You could define factorial like your standard 1 times 2 times 3 times 4 times 5 until n. You can define it over natural numbers, but what does it mean to take a factorial of 2.5? Or what is the factorial of half? Now, any math majors remain silent because most math majors would know that factorial of half is actually square root of pi. But that's under a different definition of factorial, something called a gamma function. All right, so don't bring up gamma functions. Let's just talk about honest to goodness recursive factorial. All right, it turns out that you can't easily define factorial over real numbers, whereas you can define factorial over natural numbers quite easily. Good so far? All right, so is this notion of subtyping, the basic notion of subtyping, clear? So what I mean to say is subtyping is not just a subset operation, right? So subtyping is something more than a subset operation. Okay. Now let's do something interesting. Answer this question for me. Answer this question for me. Let's take the subtype double. Let's take the type double in a computer, right? Many of you must have taken 2400. So you actually know what a double is in a computer. What's a double precision number? And let's take the subtype int, but not our natural int, not the natural number, or sometimes people say the God-given, right? A lot of mathematicians are Platonists, so they would say, oh, this is like the idealized natural number, right? The stuff that never ends, right? No, let's take the computer, our computer 64-bit integers and our computer double precision numbers. This is our IEEE standard double precision numbers, and this is our 64-bit integers, all right? Is there a subtyping relationship between these? Is there a subtyping relationship between these? What do you think? Okay, so when Laura says sort of, right? Only if you can typecast, and typecasting is not considered subtyping. Okay, so typecasting is a big no-no. Obviously, you can always typecast a real number into a natural number by truncating it and so on and so forth, right? That's not allowed. So obviously you can't typecast, right? Is there a natural subtyping relationship in the way where you can say, here is the set of real numbers, and the natural numbers are just like these special real numbers, right? Um, is that true? Well, double is a type of float, right? The difference between double and float is typically 32-bit according to the IEEE standard. And I forget, okay, I haven't taken 2400 in about 20 years. I don't want to date myself, okay? But every such number has a representation. So you have some number of bits of what's called exponent. I think it's 29-bit exponent, 22-bit 23-bit mantissa or something like that. So I forget. But you have your standard representation, right? So whereas a double precision number has like a 23-bit exponent or something like that, right? Yeah, but the problem is, here's the thing, right? In a computer, the representations matter. How you represent these numbers matter. So there is no natural way to take an integer and without doing anything, treat it as a double, right? It's not that integers are doubles without fractional parts. The way integers are represented is completely different from the way floating point numbers are represented. So you cannot take an integer like 11010000. So you cannot take a 64-bit integer and expect it to make sense as a floating point number. You can't take, okay, let me take these 9 bits and call it the mantissa. Let me take the remaining as exponent. You're going to get some random junk. All right. And so there is no natural type subtyping relationship there. So if you look at most languages like Scala, and I will show this to you in a second, integers and doubles are not subtypes. They are considered completely different types. And what you do is you typecast between integers and doubles. So for example, when you take real number division, right? So when you are dividing two numbers, x by y, and x and y are real numbers, I could, if you figured that out, I could plug in x is 1 and y is 2, and these are the idealized numbers, and I get a half, right? 0.5, 0.5. Whereas in most computers, integer division is going to be different from real number division. Integer division is going to truncate and just give you the quotient, not the remainder. The remainder is going to get truncated in integer division. Whereas in real number division, what you get is the floating point divide operator. In most computers, those are two instructions. So one of the instructions in Intel is called fdiv for floating point division. For integer division, it's the div operation. All right, so these are not naturally seen as subtypes once represented in a computer, whereas the idealized natural numbers and the idealized real numbers have a subtyping relationship. Because wherever you need a real number in an idealized function, you could always put a natural number. Yeah, it's the same thing about unsigned and signed ints, right? So most languages have a different type called unsigned int. So C++ has a different type called unsigned int and a type called signed int. In an unsigned int, what you do is you read the entire number without doing what is called 2's complement arithmetic. Whereas in a signed int, you would do something called 2's complement representation. If you've taken CSI 2400, you would know exactly what I'm talking about. Right? So there is no subtyping relationship that's natural between them. You can typecast them. You can always take a signed, unsigned int and treat it as a signed int. You can always take a signed int and treat it as an unsigned int. So you are able to typecast. So you can typecast, but you don't think of them as subtypes of each other because the algorithms you use for adding and subtracting for unsigned int and signed int are completely different. The way you treat overflows. So it gets messy. So real life gets a little bit messy. All right. So that's all I wanted to say. So just to give you this idea that, there is a difference between subtyping in the ideal world and what happens on a computer. But still, another example of a subtyping relation is any inheritance is a subtyping relation. So anytime you have inheritance between objects is a subtyping relation. So if you have your base class and you have your subclass, then wherever you need an object of type base class, you can always use an object of type subclass. So there is no subtyping relationship between a single character and a string in most languages because a character is just a 8-bit thing between 0 and 256, whereas a string is an array of characters. So most languages would distinguish, even Scala would distinguish the simple character C and the string C. Those are completely two different things. All right. So the only actual, kind of subtyping relationships we can create are the subtyping relationships between a derived object and a base object. Is that okay? So inherits from, or you can also say is a subtype of. Okay, so far. So let me then show you the type hierarchy in Scala. So it turns out Scala has a very rich type hierarchy. So let me actually show you the diagram of the type hierarchy in Scala. So if you can see my screen, uh, you can actually see this type hierarchy. And maybe I've shown you this type hierarchy before. All right. So here on the left, you can see all the quote unquote built-in types, your units, your Boolean, your char, int, short, byte, long, float, double. And these dashed arrows are referred to something called implicit conversion. So what it means is you can typecast a character to an integer in Scala, and Scala allows you to typecast them without any problems. You can typecast an integer to a long. You can typecast a long to a float. You can typecast a float to a double. But these aren't subtyping relationships. These mean that there is actually a function that whenever you have an integer, it can convert your integer into a long. There is a function which can convert a long into a float. So there is a function that can convert an int into a float by applying these two functions. Okay, and these are called implicit conversions. So I will explain a little bit of implicit conversions on Thursday. All right, so I will conclude this course by talking a little bit about what Scala does, these implicit conversions or these typecasting operations. But these aren't subtypes. The subtyping relationship that exists is between all of these types and a super type called anyval. So anyval is what is called a union type. It can be a double, it can be a float, it can be a long, it can be an int, short, byte, char, boolean, or unit. All of these take the union of all of these values, and you can view them the union as of type anyval. So for example, if you have let me give you an example, right? So for example, let's take a list with double and boolean and put them in the same list. Okay. uh, for example, Scala will let you do this. So let's take a val x1 or lst1 is list of 2.5, 3.4, 4.3. Okay, so this is a list of double. And let's do val lst2 equals list of true, true, false. That's a list of Boolean, no problem, right? You can do val lst3 equals lst1 plus plus lst2. And here's what you find. It's a list of any val. So you can put 2.5, 3.4, 4.3, true, false, true in the same list, except that it's no longer a list of double. It's no longer a list of Boolean, but it's a list of double union Boolean. And the union type, if you look at this chart of a double and a Boolean, is an anyval. So what happens here is Scala type infers LST3 to be a list of anyval. Is that okay? And so this is where union types come into Scala. Okay. And it turns out, if you look at this picture, on the right hand side, so these vals are immutable. All right. And furthermore, they are passed by value. So which means that if you have a function which takes in a parameter which is an int, then that int is actually being passed by value. All right. Whereas what happens is all your Scala classes and Java classes um, are here. Okay, and these are what are called pass by reference. So which means that when you pass a class in Scala, you do a reference. Oh, so int union char in Scala, it's going to be tricky. Let me show you what happens. So what happens is there is something called an implicit conversion between an int and a char. So let's do this, right? Val list4. I'll do implicit conversions later, but in any ways, let me do int 1, 2, 3, 4, A, B, C, D. So it still types it as a list int, and see what has happened to ABCD. They have become 97, 98, 99, 100. And that is because of this arrow, this dashed. You see this dashed arrow there? That's the culprit. So what Scala is doing is something called an implicit conversion. So this is different. So this is different. This is different. This is what is called implicit conversion or typecasting. Implicit typecasting in operation. I will explain this later. Okay, I will explain this next lecture. Okay, so this dashed arrow, and it's very important to understand. If you're going to work with Scala, it's very important to understand these things called implicit conversions. We'll do it next time. It's a good question though. All right. So here you have your type hierarchy for, okay, you have your list, you have your Java string that's actually here because a string is more like an array. All right. Yes, there is no implicit conversion from int to char. It's always from char to int because the problem is a char is 8 bits, whereas an int in Scala is 32 bits. So you can always take a 8-bit number and pad it with zeros and implicit convert it. Uh, whereas you don't have an implicit conversion from int to char. But that's only all I'm saying by that is Scala doesn't give you one by default. But if you want to write one, I'll show you how to write one next lecture. It turns out you can write your own implicit conversions. All right, and I'll show you how that works next lecture. It's also quite dangerous because it will happen behind the scenes in places where you don't realize. So I will show you how that's done, but we'll do it next lecture. Yeah, so Java is a little bit different. So yeah, I will have to look that up. Yeah, I haven't done Java in a while, but I'm not surprised. You can always do typecasting. Okay, you can always do typecasting, and I'll show this. These are a form of typecasting, and I'll show you next lecture. All right. Yeah, we'll talk about this next lecture. Today, I don't want to do typecasting, right? A typecasting is a coercion, so that's a different operation. That operation is called a coercion, right? Where you're taking a type and you're writing a function to convert it to another type, or you're coercing it to another type. Today, I'm just talking about subtyping relationships, uh, where a type can be naturally seen as something else, right? So, for example, you're here in my class and you're a computer science student, and let's say you go out and you are eating in a diner, then you are someone who is having dinner, right? So uh, it's a two different types, right? So you're of type computer science student, but you're naturally becoming, when you go out and eat dinner, you're going to become a diner, right? So no one's like typecasting you there. There's no like typecasting. Whereas uh, let's say you are currently like programming in a Mac, and you're a Mac programmer. I bring a hammer to your house and I shatter your Mac into 100 pieces. And before you say, how dare you, I give you a HP computer with Windows 95 and force you to program on it. Well, now I'm coercing you from becoming a Mac programmer to a Windows programmer, right? So there's nothing natural about it. You're just doing it, right? So it's just a funny example, but it's more like, there is a notion of an object A is an object B. A monkey is a mammal. A human is a mammal, right? So a snake is an animal, right? So you have all uh, these natural what we call ontologies, right? So something that where you don't involve like coercing, it's just happens naturally. Like you can view it this way, you can view it that way, right? And that's a subtyping relationship, whereas typecasting is a completely different beast, right? So you're talking about completely different things. Everyone kind of okay on this subtyping idea? Okay. And now you see on the top there is a type called any. Okay, so any is like the parent super type in Scala. Everything is of type any. Okay, now on the bottom, this is actually where I think this is genius. There is a type called nothing. All right, and nothing is actually what is called a type which is the bottom type. Uh, there is there can be no value of that type. So no value exists of type nothing. Okay, uh, which is different from type unit. So unit is actually a different type. Unit is a type which has exactly one value, which is a very funny value. It's the open brackets, close brackets, but it's a type of exactly one value. It's a singleton type. Whereas a nothing is actually a much more scarier type. It's a type which can have no possible value in it. And I'll show tomorrow why this bottom, this nothing is a subtype of everything makes sense. Okay, and I will use that to explain a very funny behavior in Scala with relation to exceptions or exception handling. You will see this type nothing comes in very handy. And there's also the type null, which is a dangerous type. I think it's because Scala has null. So sorry, Java has null. So Scala also has null. This is kind of dangerous because this is your null pointer kind of type. All right. You can have any class and you can have an instance called null, which is an instance of any class. Okay. We'll talk about that on Thursday as well. It's one of these untidy corners that I would like to clear out on Thursday. Oh, all right. So Sean has a great question. Does question make it somewhere in this list? Actually, no, because question is actually a very funny thing in Scala. Uh, uh, yeah, so let me answer Sean's question first, and then I'll answer your question, Logan. So question in Scala is actually just going to expand into throw new unimplemented something like this. So I'll show you. Uh, so this is essentially the statement throw new uh, not implemented error. So it's just throwing an exception saying an implementation is missing. That's what question is. It's just syntactic sugar for this statement. So anytime you hit question, think of it as executing this statement, throw new not implemented error. All right. And that's simply saying bail out and throw an exception. You could catch that exception if you wanted to. All right. Logan, nil is not the same as null. So it turns out list in Scala is defined as something like this. List in Scala is defined as a nil or a cons of an object to a list. So nil is the type of an empty list. Okay, so nil is of type list. So if I say val lst equals nil, you see it's of type nil dot type, and which is an empty list. Okay, so this is a nil is a very special object in Scala. So you define it as an object nil, which is going to be of type list. So nil is always of type list, whereas null is different. So you can say val lst equals null. So this is really different. So you can say val lst is a list of integers, which is null. This is different. This is different from nil, right? So val lst2, which is a list of integers, let's say, is nil. And now I can ask lst, is it the same as lst2? And it's false. So nil is not the same as null. It's not even a subtype of null. It's the other way around, right? From this picture, you can actually see null is a subtype of nil because null is a subtype of list. Okay. Confusing, but just follow the picture. So this type hierarchy is very interesting. This type hierarchy is very interesting. It's something that if you understood it, a lot of you can actually get a deeper understanding of how Scala works. Okay, so if with that fundamental being clear, let me ask a bunch of questions about subtyping. All right, and this is a place where I would really like you to to keep your eyes peeled, because this is where you pull one of these tricks. All right, so let us take two functions. Let's look at function types, and let's look at subtyping between function types. Subtyping between function types. All right. So let us take an example. So let us take A, and let's take B. And let's say B is a subtype of A. And now let's take an example. So let's take the function type let's say int arrow a, and let's take the function type int arrow b. So these are two types. So function type int arrow a is a function that takes in an integer and returns an object of type a, returns an object of type a. This function type is a function that takes in an integer and returns an object of type b. Okay. Now my question is int arrow b a subtype of int arrow a? So as an example, uh, let me say I require you to give me a function of type int arrow a. So I'm requiring you to give me a function of type int arrow a. Can you substitute a function of type int arrow b when I need a function of type int arrow a? Yes, very good, very good. Another way of thinking about it. So remember, let's say I have ingredients for a cake. So ingredients for a cake are going to have like flour, eggs, sugar, butter, uh, all the ingredients you need for a cake. All right. So think of the class ingredients for a cake, and let's think of a bake function as something that takes in ingredients and returns a cake. All right. So let's think of this function which takes in ingredients and returns a cake. And let's say we have something like this. So we have the subtyping relation between a cake and let's say we have, what is a good subtype of a cake? Uh, Fancy cake, right? So wedding cake, excellent. Excellent. Wedding cake. Well, bread is not the type of cake. Or what are you like one of those Queen Marie Antoinettes or something? No, 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 no. That's she got her head chopped for saying that. Okay, so you shouldn't say that, Logan. Yeah, no, no, no. Bread is not a subtype of cake. Don't say that. You will get into trouble. You know what they did to Queen Marie Antoinette, right? So let's do wedding cake, okay? All right. So wedding cake is a subtype of cake. All right. So let me say here is a function, baker. Think of a baker as a function who can take in ingredients and give you a cake. So a baker is a person to whom if you give them the ingredients, they would give you the cake. All right. Now let's think about a fancy baker who can take in the same ingredients and give you a wedding cake. So let me ask the question, is a fancy baker then a subtype of baker? Remember, wedding cake is a subtype of cake. Yes, makes sense, right? So if a person can be a fancy baker, which means they know how to take an ingredient and make it into a wedding cake, you can obviously substitute them. You can obviously substitute them for a baker. Is that okay? Good so far? So let's do the first part of, so from Liskov's substitution principle. So from Liskov's substitution principle, we say the following. Okay, we say the following. If A is a subtype of, or here, let me take this picture. If B is a subtype of A, if B is a subtype of A, then the function type T arrow B is a subtype of T arrow. Good so far? All right. So let me now ask a different question. All right. So let me now ask a different question. Let us say we have, you know, uh, let's say we have a different subtyping relationship. Okay. So now let me give you a different question. Okay. So let me give you a different question. Let us say that X and Y have a subtyping relationship. So, and here's the thing, I don't want you to think of this in terms of X and Y. I will give you concrete examples to develop your intuition, okay? So this is going to be somewhat tricky. So let us think of X and Y, where Y is a subtype of X. So Y is a subtype of X. And now I'm interested in a function that takes in X and returns some type T, or let's call it int, and another function that takes in Y and returns type int. And the key question I want to ask is, does this work? Is there a subtyping relationship between y arrow int to x arrow int? Or is the subtyping relationship in the opposite direction? All right. So this is the key question I want to answer. So which direction does the subtyping relationship go? All right. So let me now give you a different analogy for that will help you think about this. And this is my favorite analogy. I used to do martial arts. So so let me give you this analogy. Okay. So as an example, uh, any person, and let's say I have a subtype of any person, which is going to be out of shape. I will tell you where I'm going with this. Okay, so you have the set of all people, and a set of very special people like me who are out of shape. All right, who haven't exercised in a while, and who like eating cakes, right? Too many cakes. So now you have out of shape people and any people, and it's obviously there's a subtype relation. All right. So let's think of in the martial arts context. Let's think of a black belt master, like a uh, black belt can take any person and fight them. All right. So a black belt is someone who can. It's a function where if you input any person, they are able to fight them, right? And that's a true black belt master. Whereas take someone who is a white belt, and this can take in an out of shape person and fight them. Okay. So remember, a black belt can take in any person and fight them, whereas a white belt or is someone who can take in an out of shape person and fight them. All right. Don't be fooled by which one I drew on the top and bottom. In which direction does the subtyping relationship go? Does it go from the white belt to the black belt, or does it go from black belt to the white belt? So now imagine, yeah, so good. So imagine you're requiring your requirement is a black belt. Why do you require a black belt? Let's say you are shooting a martial arts movie, uh, and you have all your all the people lined up, and you have your shoot lined up, and let's say Bruce Lee is Bruce Lee is passed away a long time. Let's say Jackie Chan is out sick, so you need a black belt to do the fight scene, right? So that's why you require a black belt. And let's say I offer you myself, let's say a white belt. Will this fly? Do you think I can shoot a movie? Would you watch the movie? No, right? So this is not going to fly. Whereas the other way around, let's say my movie is about a poor kid, like it's Karate Kid, and it's the beginning of Karate Kid, right? Where the kid doesn't know anything, right? So I'm really requiring a white belt to shoot my scene, and I'm providing you a black belt. Just don't get too academic on me, or don't get too martial arts on me, right? So can I do the substitution this way? Yeah, they're all good actors, let's say. Yeah, right. So if I knew how to fight any person, I could always fight an out of shape person. That's another way of putting it. So the the direction of the relationship is the other way around. So even though an out of shape person is a subtype of any person, a function from any person to fight is a subtype of a function from out of shape person to fight. So let me give you another example, like a more practical example. All right. Let's take an example of a document, which can be any document. And let's say you have a PDF document as a subtype, or Word doc, or a text doc, right? So you have all these types of documents as subtypes. All right. Now let's look at you know any printer. Any printer is a function that can take any document and print it. So let's just say it outputs a string. That's the printed version of the document. Whereas let's take a PDF printer that can take just a PDF document and output a string. Now tell me, in which direction does the subtyping go? Does it go from any printer to PDF printer, or does it go from PDF printer to any printer? Which direction does the subtyping go? Any printer to PDF printer. Apply Liskov substitution principle, right? Why? Okay, let's do the Liskov substitution principle test. So my requirement is I want to print a PDF file. So I want a PDF printer. And you are providing me any printer. Is this okay? Do you think you can make that work? Why not? You asked for you are asking for a PDF printer. So you have a PDF file, you want to print it, right? And I give you this any printer, which is the Swiss Army knives of printers, right? It can print anything, right? So it can print anything. It can print a PDF, it can print a Word, it can print a text, right? So if my requirement is just a PDF printer and you provide me with any printer, that should be fine, right? Think about it. It has more capabilities, right? So this has more capabilities, more capable. Exactly, Logan. Is that okay, John? No. So that's the difficulty in seeing this, right? So what you have to see is any printer is actually more like a printer that can take in any document. So it can input any document and handle it, convert it to a string, right? Whereas a PDF printer is more restrictive. It can only take in. So the substitution goes this way. If you require a PDF printer, you can substitute any printer. But let's say your requirement is an any printer. I want this any printer that can print any document type I choose, PDF, Word, or text. And you try to sell me, you as a person who's expert in printers, you are trying to sell me a PDF printer. Should I buy it? Do you think it will work? No. So when you apply Liskov substitution principle, you see that it's actually funny. So it's actually funny. So what's happening here? So if you have X and Y, where Y is a subtype of X, then you actually see that a function from Y to T is a supertype of a function from X to T. So this function takes in more inputs, including Y, whereas this function takes in fewer inputs. So what you see is that the relationship gets inverted. So even though Y and X are in this way, where Y is a subtype of X, when you look at input side of the function, you see this. X arrow T is a subtype of Y arrow T. And I gave you two examples of this. One example where was this is document, and this is a subtype which is PDF document. Another example I gave is this is any person, and this is an out of shape person in terms of like fighting, right? So you can actually see the following. right? So when it comes to function types, let's say uh, a and b are in this way, and x and y are in this way. So is a subtype. Then you say a function from y to a and x to b. This is a subtype. So if you look at the output side of things, this is called covariant. And I'll explain what this means in a second. This is called covariant. So covariant, co means in the same direction as. So just as the relationship between A to B is, so is the relationship between the outputs of a function. Whereas for the inputs, the relationship is inverted, and this way is called contravariant. Contravariant. So the inputs to a function are contravariant, which means that if y is a subtype of x, then x arrow something is a subtype of y arrow something. Is this clear? Is this principle clear? So it's clear when you break it up into two parts. When you break it up into just keep the inputs the same, let's look at two different outputs, or let's keep the outputs the same and let's look at two different inputs. And you immediately see how the subtyping relationship starts to work from that. Okay, so Laura, which part is confusing you? Let me try and re-explain this. Or was this answer to a previous question? This is kind of important, right? So the understanding this for subtyping is super important. But hopefully this makes sense when you think about it from the point of view of Liskov's substitution principle. Oh, okay. Uh, okay, let's go back to this, right? Um, right. So you're right. And any printer would be a subtype of so many different printers, but it's not object inheritance, right? So it's not object inheritance. So Kai, you make an excellent point. It's not object inheritance. This is subtyping. This is honest to goodness subtyping, right? So that should be, that is quite important. The other thing that Scala does, which is very sneaky, is let me actually show you. So there is something else that Scala does. To your point, Kai, which is an excellent point. There's something else that Scala does, which is why you have this type called nothing. So it turns out that even though your any printer is a subtype of so many different printers, they are all going to converge back into something called a nothing printer, right? Because it kind of inverts the relationship. This is kind of complicated, but the simple answer to your question is it is not object inheritance. So you don't have to worry about multiple inheritance here, right? Multiple inheritance is not a thing for this. Okay, so if everyone's okay with this, I will, yes. So null is a kind of nothing from the diagram. Yes. No, the other way around, right? So let's go back. Let's go back to this. I was running too fast. Sorry. The other way around. Let's look at this. So nothing is a type of null. Okay. So this is the direction. But for example, you would never write this. Okay. So you would never write this. I will try and explain this more next time. You would never write a function from null to int, for example, or a function from nothing to int, right? So you would never have null or nothing as the input types. Yeah, I wouldn't go that far, Logan. So I wouldn't try I am not going to try and actually make sense of this. Okay, this is just a definition in Scala. So Scala defines a type called null, which is going to be a subtype of all the things that are passed by reference, and it's going to define a type called nothing, which is going to be a subtype of everything. These are totally definitional. Okay, and I'll explain the reason why nothing exists, or Well, that's in your philosophy class, right? Ask your philosophy professor, why does nothing exist, right? Um, and then they will say, oh, nothing exists, and then you say, well, something exists, and you can try and tie them into a loop. But I'll explain why this exists next time. Okay. Yes, you could. I mean, so none of these talks about mixins, right? Mixins are kind of entirely like orthogonal, and they would complicate the picture a little bit. Okay. Yeah, that picture would be quite complicated. But if you have questions like that, we can talk about it. Yeah, yeah, you could do that. You could do that. All right. So maybe I should stop here and give everyone 10 minutes today to fill out your FCQs. So please do that. I'm going to be around to answer further questions. Okay.